Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. Today I want to talk about the Hilbert symbol, which is an extremely important tool in number theory because it connects numbers in the field with this rather mysterious arithmetic invariant called the Brauer Group. Okay, so recall that the Brauer Group is formed from the elements which are central simple algebras over some field that you have K. That's our symbol for our field K. And they're equivalence classes of these. And the amazing fact about this is that when you tensor product two central simple algebras, you get another central simple algebra. So you can use this as the basis of a group multiplication. Okay, so you have to look at equivalence classes to make sure that you get a group structure out of this, but otherwise it's very, very naturally defined. Okay, so how do you actually get central simple algebras? Well, one way we can do that is to look at these quaternion algebras. So let's just recall how that works. If you're given two non-zero elements A and B inside our field, what you can do is you can construct a K algebra with generators I and J. And let's just see how these generators are related. So first, the I squared, it's given by that first entry A. J squared is equal to B. And at the moment, we need to do something to say how I and J multiply. So the key point here is that the non-commutativity is given by the fact that these skew commute. So Ji is equal to negative Ij. Okay, so if you're given two of these, okay, so what we want to do is I want to have a look at some of the properties of this. And we want to kind of think of this as a function of A and B. So we'll fix the field K and look at this as a function of A and B. So the first thing to note is that, well, I and J, they're just symbols for generators. You can swap them around. And if you swap them around, what will happen? Well, basically what you'll find is then instead of getting A, B, K, that quaternion algebra there, you'll get B, A, K. And of course, swapping the generators gives you something that is isomorphic. So basically, A, B, K is isomorphic to B, A, K. Okay, so this is a symmetric sort of a function in A and B. So the next thing is, well, what happens if you try to take the tensor product of two of these quaternion algebras? Well, in general, this is quite a complicated sort of a thing, but there is a special situation where we can say more about it, and that's the following. Suppose we have ABK, tensor AB prime K. So the key point here is, let's suppose the first entry is the same. Then, in this case, we have a very, very nice formula for what this is. So firstly, note that this algebra here is four-dimensional. This is four-dimensional, so you'll get something that is 16-dimensional. And so how do you get something that's 16-dimensional? I claim it's the following 16-dimensional thing. It's this four-dimensional algebra, just 2 by 2 matrices in K, times this four-dimensional algebra here, which is a quaternion algebra that's easily written in terms of the A, B, and B prime here. And it's just given by a BB prime. Okay, so that's a rather nice formula. Okay, and one way to think about this, so remember when you're looking inside the Brauer group, this is equivalent to just if you change something by a full matrix ring, it doesn't change, you get something equivalent in the Brauer group. Okay, so that's just equivalent to just this one here. Okay. So let me just suggest to you why this is true. It's a beautiful formula. Unfortunately, you can't have a more general formula, and that's part of the subtlety of the Brauer group. But in this case here, you do get this lovely formula. Okay, so let's write down this AB prime K. Okay, so what we'll do is we'll use some symbols for it. Okay, so as usual, it's given by two generators. So let's call them I prime and J prime. Such that I prime squared equals A, J prime squared equals B prime, and then the J prime and I prime skew commute. Okay, so what are we going to do? So what we're going to do to prove for you, I won't give you the full proof, but I want to suggest to you why it's true at least. Okay, and the way we're going to do it is as follows. So inside this tensor product here, I want to find a subalgebra. Okay, so to find a subalgebra, of course, you have to have the copy of the field. So that's K times the unit is 1 tensor 1. And then I'm going to throw in I tensor 1. That's something that's inside here because this is just the algebra over K generated by ij and I prime j prime. Okay, and the copy of I is I tensor 1 inside here. Okay, and then we're going to also have j tensor j prime. And then we're going to have the product of these two. So the product of these two, you multiply the I times the j, you get an ij here, and 1 times j prime, you get the j prime here. So that's the product of those two. Okay, and I claim that this set, the span of these four elements, is actually closed under multiplication. Okay, so that's quite easy to show why that's true. So let's, for example, square the first term. Is it still inside here? Well, when you square the first term, you get I squared tensor 1, which is just, well, I squared is equal to A. So that's A times 1 tensor 1. Okay, what about this term here? When you square J tensor J prime squared. So you get a J squared, which is a B, tensor, and a J prime squared, which is a B prime. So this is B prime times 1 tensor 1. And the other thing that you'll note is that, well, okay, so that means that when you play around with these and you look at the algebra generated by this element and this element, okay, you don't need to go to higher powers than 1. Okay, but what about how do they multiply together? Well, if you just multiply this one with this one, we saw we get this one. But what about in the reverse direction? So J tensor J prime times I tensor 1. Well, of course, well, the I skew commutes through this J, so you'll get a negative sign, but the 1 commutes through the J prime. So this is just negative of I tensor 1 times J tensor J prime. So the key point here is that this I tensor 1, it squares to something in the field. This J tensor J prime squares to something inside the field. And these two generators skew commute. Okay, the product is this one here. So we actually get a nice quaternion algebra. And let's see which quaternion algebra do you get? Well, I tensor 1, when we square it over here, we got A. So that's why you get an A here. And this J tensor J prime, when you square it, you got B prime. So that's why you get the B prime there. Okay, so that's very nice. So what we found is inside this tensor product, we have a copy of this um, quaternion algebra. So of course we want to show that the tensor product is a tensor product of this quaternion algebra with 2 by 2 matrices. So now I want to find the 2 by 2 matrices inside there. And of course inside this tensor product here, these two copies of the algebras, they commute, okay, because M2K inside here is the things of the form M2K tensor 1, and things inside this one here are of the form 1 tensor, things inside that quaternion algebra. Okay, so I won't go through the complete proof of that second algebra, but it's given by this here. Okay, so firstly you need a copy of the field. Okay, and then you've also got 1 tensor J prime. You've got I tensor I prime J prime, and then you've got the product of these two. Okay, so you've got an I in the front here, J prime times I prime J prime. Okay, so that's a little bit more complicated. The J prime skew commutes through the I, so you get a minus sign here, and the J prime squared gives you a B prime, and then you've got the I prime left over. Okay, so that's a product of these two. And you can check that this is a quaternion algebra, but this quaternion algebra is actually split. So if you do a little bit more work, you can actually show it's a split quaternion algebra. So it's isomorphic to 2 by 2 matrices in the field K. Okay, great. So what's the final part is, well, inside this algebra, okay, so this is the tensor product, A, B, K, tensor A, B prime K. Okay, we've got, firstly, you can include the algebra A1 in there, and the algebra A2. And in fact, since these two algebras commute, you can just do the multiplication map. Okay, so if you have something inside here, A1 tensor A2, you can just map this to the product A1, A2. Okay, and why can you do that? For you to be able to do this, you need the fact that the copies of A1 and A2 inside here actually commute. And you can check this fairly easy. For example, this one here, this term here, okay, this commutes with, or maybe I'll use a different color here. this term here commutes with this term here. Okay, so the j prime of course commutes with the j prime because they're the same. So of course 1 tensor j prime commutes with this one, and similarly 1 commutes with ij, and j prime commutes with this j prime, so they commute as well. Okay, so you can check individually that these commute, and so of course you've got a homomorphism from this side to this side. Okay, and of course since A1 and A2 are subalgebras, it's going to be injective on at least A1 and A2. And remember, the left-hand side is central simple, so the kernel has to be trivial in this case. So now when you do a dimension count, of course, since the kernel is trivial, okay, and the dimension can only on the right hand side, the dimensions on both sides are the same, so actually it has to be an isomorphism, and that gives us this lovely identity here. Okay, and the important thing that I want to take away from this theorem is, firstly, as a function of a and b, this is symmetric. Okay, and also inside the Brauer group, if you have AB and you multiply AB prime, you essentially just get this wonderful form A BB prime. So if you fix the A, you basically have just a group homomorphism in the second variable. Okay, so it's additive in that second variable. Okay, so let's move on to the next slide to make this more formal, and it says a lot more facts about this symbol. Okay, so remember, I want you to think of that quaternion algebra, that symbol, as a function. Okay, it's really a function. So let's just write that out formally. So if you have an element of k cross k cross, so that's a pair of non-zero elements in your field, we're going to map it to what? You have this central simple algebra, this quaternion algebra ABK, and you look at the equivalence class of that. Okay, so remember, two central simple algebras are equivalent if they're what's called Morito equivalent, or basically they just differ by some tensor product of matrix algebras. Okay, so you can matrix algebra them both up to become isomorphic. And what's the key point of this theorem? So the key point of this theorem is as follows. Phi is, well, remember what happens is that if you have phi of, or maybe I'll write it out more precisely first, phi of AB, and then that's in the Brauer group. So tensor product is multiplication times phi of AB prime is equal phi of ABB prime. So that is phi is, well, firstly, the first fact is phi of AB, also phi of AB equals phi of BA. So is symmetric and bilinear. Okay, so that's the first point, is it's a symmetric bilinear form. Okay, so that's rather nice that you have a symmetric bilinear form on this. Okay, the values are in this rather funny group here called the Brauer group, but nevertheless you have some symmetric bilinear form, and this form is going to tell us a lot about elements inside here, the arithmetic of that field. Okay, so let's look into this a little bit closer. So suppose we have AB squared. Okay, so AB squared is so what's that equal to here? This is isomorphic to M2K. Okay, so that's something that we saw before, is true. But what does that mean? So remember, what this means is that phi of AB, so since this is bilinear, this is just phi of AB squared equals 1. Okay, so that's what it means. Okay, by bilinearity, this is just is equal to phi of AB squared. But we know that this is actually, since you've got a square here, once you have a square here, then this is going to be a split quaternion algebra, so it's just 2 by 2 matrices in K. Okay, so that means that, well, where does this actually, so what is this phi of AB? So this phi of AB is actually an element of, not just in the Brauer group, but it's in an element of the Brauer group whose square is trivial. So it's in the what's called the 2 torsion of the Brauer group. Okay, so this is a very important conclusion that I want to write down. Okay, so this function phi, normally we don't use that um, notation. We just write it down using the usual symbol notation. So firstly, it's a symmetric bilinear form. And it's a symmetric bilinear form on what? So firstly, it's certainly true it's a symmetric bilinear form on k cross. But the thing is that it's trivial on squares. So if you multiply by a square, it doesn't make any difference. So um, it doesn't depend on uh, the element of that field, that non-zero element on the field, except up to squares. Okay, if you change this the second value by some b squared, you'll only change it by some m2k, so that's not going to change it inside the Brauer group. So that's the first point. And the second point is that where does it land? Well, we just saw that this 5ab lands inside the 2 torsion. The 2 torsion, which is Brauer group, and you put a subscript 2 here. Okay. So what we see is that, in fact, it's going to be a symmetric bilinear form on an F2 space, this one here. Okay, so let me just explain briefly what's going on. So initially you have this bilinear form, which maps to, well, first we saw that it maps just to the Brauer group of K, but we found that it always goes to the 2 torsion, that subgroup of 2 torsion elements. The other thing we saw is that it doesn't matter if you change this element of K by some square. So you might as well just factor out by the squares here. Okay, so you've got an induced symmetric bilinear form on K cross the multiplicative group of K modulo the multiplicative group of squares. But what is this? So this K cross, it's an abelian group, although the multiplication is written with a multiplication, not an addition. And so it's a Z module. And then what you're going to do is you're going to factor out by all the squares. So this is, in fact, a Z mod 2 module. So that is, what's Z mod 2? It's just really Z mod 2. That ring is the field F2. So basically, it's a vector space over the field with 2 elements. Okay, so this is also a vector space over the field with 2 elements because you're looking at 2 torsions, so 2 equals 0 here. So basically, working over the field with 2 elements, you have a bilinear map from this vector space here. Okay, a bilinear map from this F2 vector space here to this vector space over F2 here. Okay, and that's a bilinear map. So this is going to be very, very important to study arithmetic of the field K. Okay, so what can we say about the Brauer group? So the Brauer group is often difficult to compute, and I want to give you now a major theorem in local class field theory. I won't be able to say what the proof of this is, but at least I can state what it is. So in number theory, we're often interested in p-adics. Okay, so if you don't know too much about them, do have a look at my video about p-adic numbers. And so we're going to look at the p-adic rationals here. And so one way to think about what are the elements of the p-adic rationals, just to remind you, is you can think of this as the set of what? They're just Laurent series in P. So you can look at the set of all, uh, you'll need some coefficients, so maybe a n p to the n plus a n plus 1 p to the n plus 1 plus a n plus 2 p to the n plus 2 plus dot dot dot. And this these AIs are, where are they? They're in 0 up to p minus 1. And these n is just some integer, so it could be negative. Okay. And so basically this is just a Laurent series in powers of p. Okay, so the powers of p can be negative or positive. So you always start somewhere, but it can go off, shoot off to infinity. And this is a ring, and it's actually also a field. So non-zero elements you can invert, much as you can invert usual Laurent series. Okay, and this is a field, and the thing that you have to realize is that actually Z embeds inside this, and in fact Q embeds inside this. So that's the other important Okay, so Q is contained inside there. So how do you contain Q inside there? So I guess the key point is that, well, how do you put Z inside there? Well, to put Z inside there, you can always do a base P expansion, and that gives you some polynomial in P, in fact. Okay, all the integers are inside there like that. And then, well, why is Q inside there? Well, this is a field. Okay, so you can invert things like, well, certainly we can invert P. That's easy because P inverse is in there. But you can also invert things which are prime to P as well, which are non-zero. Okay, so that's the p-adics, a brief recall of the p-adics. And in this case, the Brauer group is what abelian group? Well, it's this one here. It's just Q mod Z. Okay, so Z is a subgroup of Q, and that's what you get there. Okay, so far I've only mentioned another Brauer group, so that's the Brauer group of the reals. And just to remind you what that is, there's only one non-trivial division ring over the reals, which is central over R, and that's the Hamiltonians, so Hamilton's quaternions. So there are only two elements in this Brauer group. So this is just a cyclic group of order 2. Okay. So one of the things that you might want to see is that inside here, okay, so what types of other elements inside here? For example, it has a subgroup which is generated by half plus Z. Okay, and you think, what's the order of this? Well, when you double it, it's going to be equal to double this generator here. You'll get 1 plus Z, which is just Z, so that's trivial. So this is just isomorphic to Z mod 2. And in fact, that's a 2 torsion inside here. So let's just note that the Brauer group Q hat P, if you look at the 2 torsion, is isomorphic to Z mod 2. Okay. So I don't want to say too much about why this is true, but I want to give some sort of motivation for uh, where this comes from, or try to demystify it a little bit for you at least. And it's the following reason. So are you able to say, for example, what uh, central simple algebra corresponds to the following element of Q mod Z? Okay, so there should be some non-trivial central simple algebra or division ring associated to that. Okay, so let me tell you what it is. It's a cyclic algebra, K sigma. Okay, so maybe I'll put here F. That was perhaps the notation I wanted to look at. Okay, F sigma, and then basically you need an nth root of something, and the nth root of something that you're going to put here is, oh, let me do this for yeah, so you put here P, and so P is this prime here, P, and you need this to be a cyclic extension, and you need an element of this sigma. So F over Q hat P is cyclic degree n. So to understand this explanation, you'll need to know a little bit about number theory and Gauss theory. So what's the point of that? So which extension is this? Well, it basically corresponds to cyclic degree n extension. Um, let's call it F bar, F over just bold F over F P of degree n, and sigma corresponds to Frobenius. Okay, so the key point is that, well, so if you have a finite field, you know all about the cyclic extensions. So this is some things that you might learn in a Gauss theory course, and you can find a cyclic extension of degree n. Okay, so in the case when n equals 2, you can find a finite field which is a degree 2 extension of Fp. Okay, and then that's the one that's going to be used here. Okay, and so once you find a extension of this, so what's the relationship between this and this QP? Well, remember you have the p-adic integers, and basically if you mod this by p, this is isomorphic to fp. So to create this field extension f, you basically add to this fp some alpha. So what you can do is this alpha you can lift to this z hat p, because this fp is inside here. So basically you can lift this root, okay, to this p-adic situation using Hensel's lemma. And then that extension you can pass to the field of fractions q hat p to give you f. Okay, so I won't comment more about this because really this requires a bit of Galois theory. Okay, but it shows you at least where these elements, these non-trivial central simple algebras over this field come from. Okay, and the key point is that, well, the one that corresponds is half z. Okay, what does it correspond to? So basically it's the cyclic extension, and what you basically want is you want a degree 2 extension of q hat p, which comes from a degree 2 extension of fp. Okay, so finally we can talk about the Hilbert symbol. Okay, so the Hilbert symbol, the cases we're going to look at is where k is either this q hat p or the reals. So when it's the reals, the Brauer group of k is isomorph to z mod 2, so that's also true of the 2 torsion. And we saw before that also, what is the 2 torsion inside this in general? So remember this Brauer group, the theorem, this major theorem in local class field theory, said that this is isomorph to q mod z. So which are the fractions that when you double them, okay, that gives you an integer. So I guess the only thing you can have in the denominator is a 2. So modulo z, you just get the 2 torsion in here is z mod 2. Okay, so since it's a cyclic group of order 2, you can also identify it with 1 and minus 1. And that's what we're going to do. We're going to identify this. So remember we had this map. The symbol map it's a symmetric bilinear form on k cross mod k cross squared to this 2 torsion in the Brauer group. Okay, and basically that is the Hilbert symbol. Okay, so to be more precise, what is it? Okay, so suppose you want to look at the Hilbert symbol for prime p. Okay, so this is what you do is you look at two elements a, b inside this p-adic rationals, and then a, b, p, so that's some quaternion algebra, and you can think of it inside this 2 torsion in this Brauer group, and hence inside this set here, so it's either plus or minus 1. Okay, so it's this symbol here. Similarly, if a and b are real numbers, then we have the Hilbert symbol, and now in this case we think of r as an infinite prime corresponding to an infinite prime, so we have a subscript infinity there, and this is going to be just this element of that 2 torsion in the Brauer group. Okay, so what I'll do now is I'll just show you how all this theory that we've been talking about works in the case of k equals r, because that's fairly simple to see what's going on. Okay, so remember you have this bilinear form on r cross times r cross squared. Okay, so what is r cross squared? Okay, so of course if you square any real number it's going to be positive, so this is just the positive reals. Okay, so it's all non-zero reals modulo all positive reals. So of course this is isomorphic to, well, basically it's either positive or negative. Okay, when you do the quotient, all you remember is whether it's positive or negative. So as a vector space over F2, these are both just one-dimensional, okay? And this is mapping over to the Brauer group of R. I don't need to do the 2 torsion because this is already 2 torsion, okay? So remember this is a bilinear map, so if you put the trivial map inside here, you'll get 0, or the trivial element in here. So if you have positive and anything you like, this gets sent to 0. And the only interesting question is what happens when you have negative, maps to negative. Okay. And this is the non-zero element, the quaternion, Hamilton's quaternions, or rather the the equivalence class containing that. Okay, so that's how this bilinear form works in this case. It's non-trivial, okay? If you put negative number, comma negative number, it's going to be the same as -1, comma -1. And as we know, that's how we constructed Hamilton's quaternions, okay? But if you have positive, so remember it's symmetric, this bilinear form. If you have positive things in either slot, you're going to map to 0. Okay, so this is going to be an important tool, this Hilbert symbol. In the next video, we're going to link this up with the notion of Legendre symbol and also show how Hilbert generalized the quadratic reciprocity law of Gauss to his Hilbert reciprocity. I hope you enjoyed this adventure in pure mathematics.